Okay, it's recording now. So last time I talked about the synchronous counter. Okay, we have seen the drawback of the ripple counter is that there's a delay in the flip-flops, and these delays are going to increase, okay, from one bit to another. And for this reason, you don't really get the count bits at the same time. So therefore, this delay is going to increase according to the number of flip-flops, according to the number of bits that we have in the counter, and this is not good. So the ripple counter is not a truly synchronous counter. Maybe I need to refresh your memory about this. So we have seen three different implementations. Okay, we have seen an implementation of the ripple counter, which is shown here, right? You can see, can you see clearly my slide, my presentation? Is it clear?
Yes.
Okay. So notice that we can implement it using positive edge triggered flip-flops, but we need to connect Q prime. So these are D flip-flops, okay? And we are connecting Q prime back to D, and also we are connecting it to the clock input of the next flip-flop, okay? The same thing here for Q1 prime, back to D1 and back to the connected also to the clock input of the next flip-flop and so on. So this is a ripple counter. Okay, there is a ripple counter and it is using the positive edge. So notice that when Q prime goes from 1 down to 0, okay, so when Q prime goes, for example, when the Q prime goes from 1 down to 0, from when Q goes from 1 down to 0, the Q prime goes from 0 to 1. And this is when we toggle the value of a Q1. The same thing can be said about Q2 and Q3. Now we can implement this, okay, we can implement this as shown in your textbook. The textbook actually shows negative edge triggered flip-flops. I talked about this last time. I added a slide about the figures which are shown in your textbook. So notice that the textbook is using negative edge triggered flip-flops. So it's showing here two implementations. Let me use here my pen tool. So all of these here are negative edge, okay, negative edge, okay. This is the clock here, negative edge triggered flip-flops. So this is my clock input. And notice that we are connecting here the Q. So here the Q is showing as A0, A1, A2, A3. This is my Q output. Notice that the Q prime is connected back to D so that we can toggle. So that's Q prime is connected back to D. Q prime is always connected back to D to toggle. But we are connecting A0 to the clock input of A1. And the clock input here is negative edge triggered flip-flop. Let me use my eraser. Okay, so for some reason we got this. So I hope this is clear. Okay, that's a different implementation using negative edge triggered flip-flops. Okay, whereas in the previous one we're using positive edge, so these are negative edge triggered flip-flops. And notice that Q, not Q prime, is connected to the clock input, okay, of the next flip-flop. That's because we are actually here changing when the Q goes from 1 down to 0, then we toggle the value of A1, okay, of the next flip-flop. We can also implement this using T flip-flops as indicated in the second diagram by connecting here logic 1. So rather than connecting Q prime back to the D input, we are using T flip-flops, but the T flip-flops are more expensive because they use XOR gates at their inputs. So it can be implemented using D flip-flops with XOR, but we can also implement the ripple counter using the T flip-flops. I don't think this is actually better, okay? This is not really better because the T flip-flop is more expensive than the D type. And we can do it with the D type by toggling, by connecting the Q prime output back to the D, okay? So for this reason, there is no really advantage, okay, to implement. Now, in other counters, there is an advantage of using the T type. I will show you this in the synchronous counter, but in the case of the ripple counter, now the ripple counter is not really truly synchronous, but we can use the T flip-flop or even the JK. The JK can also be used, but we are actually increasing the cost of the circuit. Okay, so we have seen this in my last lecture. We have seen also the timing of a ripple counter. So notice that how the delay is increasing. Okay, so Q0 is delayed by delta, Q1 is delayed by 2 delta, Q3 is delayed by 3 delta to jump from 0 to 1. And finally, this is Q2, and the Q3 is delayed by 4 delta. So we start with delta, then 2 delta, 3 delta, 4 delta. So here, delta is the flip-flop delay. Okay, that's the delay inside the flip-flop from the edge of the clock until we change the output of the flip-flop. So notice that how this is going to increase in the case of the ripple counter. I did not really find this diagram in the textbook, but I already have it. I taught this course from previous semesters, okay? And this actually clearly shows the drawback of the ripple counter. So for this reason, designers don't like the ripple counter, although it's very simple and very easy, okay? So because of this rippling effect, okay? Because of this rippling effect, which is shown clearly in the timing diagram. So do you have any question about this? Is this clear? It's better actually to raise questions now, because if you understand the topic now, you will actually make it easier for you to understand and to prepare yourself for quizzes and for exams. All right, no questions? Fine. So for this reason, okay, as I said, this kind of rippling effect, and because the delay increases from one bit to another, this is why people don't use the ripple counter. So what do we have? We have the synchronous counter. And the synchronous counter is very simple. We use an n-bit register. Okay. Again, I'm checking your textbook. Okay. But again, I find that this is a very simple description. This diagram is not in your textbook, but it helps you to understand the meaning of the synchronous counter. It's very simple to understand. So we have an n-bit register. So here we have n flip-flops. This will be an n-bit counter. Notice that all of these flip-flops are connected to the same clock. They are also connected to the same reset input. So we can reset all the flip-flops inside this n-bit register, and therefore we can reset the Q output here, consists of n bits, we can reset it to 0. So how do I count? All what I need is just an n-bit incrementer. That's a pure combinational circuit. So the incrementer here is going to add +1. It's very simple. You can think about it at a high level. It's not really that difficult to build a counter. It's really that simple. So take this Q and add to it +1. So this becomes Q +1. So for next cycle, we are going to increment the counter inside the register. As simple as that. Okay? That's synchronous. And it is synchronized with the clock. Okay, is this clear? Now, how do you implement this incrementer? So the n-bit register, so this is actually 4-bit. I'm showing it with 4 bits. So notice that we have 4 flip-flops. Okay, so notice that the outputs here are Q0, Q1, Q2, and the Q3. These are the outputs of the flip-flops, and they are also the output of the counter, because this is my 4-bit counter output. So we use the output of the flip-flops as the output of the counter. Now, what I need to do is that I need to implement my 4-bit incrementer. My 4-bit incrementer. So how do you implement the 4-bit incrementer? Well, you just use actually an incrementer circuit. That's it. Okay. So the incrementer circuit consists of what? Half adders. Already we have studied half adders before, remember? So notice that how I actually put things together. I get things from something that I already have seen before. So this is a half adder. And if you look here at this incrementer, it actually is an adder. So this is a half adder here. This part here is a half adder. It consists of XOR gate and an AND gate. This is also a half adder. and so on. Okay, so these are half adders. So if this enable equal to 0, then basically we're not really adding anything. Okay, so if this enable equal to 0, so basically you get the D inputs is equal to the Q output. So D becomes a Q, D0 becomes a Q0, D1 becomes a Q1, and so on. That's when enable equal to 0. Because you are XORing with 0, okay, you get basically D0 equal to Q0. Also, C1 will be equal to 0, C2 will be equal to 0 because we're using AND gates. When you end with 0, you get zeros. And notice that when you XOR with 0, D1 becomes a Q1, D2 becomes a Q2, and so on. So therefore, we are not going to change the Q output. So if I would like to freeze the counter, this is the importance of this enable. So this enable, if it's equal to 0, this is actually my enable input here. If it's equal to 0, it means that freeze the count. Do not count, okay? So remain in the same count value. If enable is equal to 1, basically we're adding 1. So think about enable as a carry in. And this is actually is your carry out. This is just an incrementer, right? Just adding plus 1. So if this is equal to 1, right, you are adding plus 1. That's it, okay? That's basically your 4-bit incrementer. And basically you get the D input is equal to the Q output plus 1. تفضل عبد الملك. عبد الملك، يس تفضل.
يس دكتور، بس عندنا ديلي داخل الانكريمنتر نفسه.
صحيح. But basically all the what you are saying is true. Yes, what you are saying is true. We have actually a delay inside the incrementer itself. So basically, in order to generate these carries, let me here. So here we have C1, here we have C2. We have to propagate these carries, right? And there's a delay. Okay. But remember that, okay, all of these delays are within a given clock cycle. But at the same edge of the clock, all the flip-flops are going to change at the same moment in time.
Okay, but maybe there is.
So let me explain this again. Okay, so the C1, C2, C3, all of these are going to change within a clock cycle. And of course, because we have actually we are propagating these carries, the delay is going to increase in the 4-bit incrementer, but that's a combinational circuit. So we get here the D inputs at different times. We get here the outputs of these XOR gates because the C1, C2, and so on are going to propagate. We get these D inputs at different times, not at the same moment in time. But all of them are going to wait until they see the rising edge of the clock. At the same rising edge of the clock, we change all the outputs at the same time. That's what's important. Okay, Abdul Malik?
Okay, it's clear now. Thank you.
Right. Okay, good question. Do you have other questions? Anyone has a question? So that's my 4-bit synchronous counter. Now let me show you something, is that you get C1 is equal to 1. Of course, if it is enabled and Q0 equal to 1. There's an AND gate here. Notice there's an AND gate. So basically, if you have Q0 equal to 1 and it is enabled, then we get C1 is equal to 1. When do we get C2 is equal to 1? We get C2 equal to 1 when C1 is equal to 1 and Q1 is equal to 1. Let's actually mute this, okay? So let us see again. Yes, Abdul Malik, you have a question? Are you raising still your hand? Okay, right. So again, let me just clean up this a little bit. Erase. Okay, so now suppose that we enable this counter. Okay, good. We are enabling this counter, so we have here +1. That's meaning of enable. So when do we get C1 is equal to 1? When we have a Q0 is equal to 1, right? So when we have a Q0 is equal to 1, we are going to actually have C1 is equal to 1, and we are going to toggle the value of a Q1. So therefore here we are going to toggle because we are using XOR gate. So when you XOR with 1, you toggle Q1. So if Q1 equal to 1, you get 0. If Q1 equal to 0, you get 1. So basically, you will toggle when you get C1 is equal to 1. Right. When do you get C2 is equal to 1? You get C2 is equal to 1 when you have both, okay, Q1 and Q0 are both 1, 1. So you must have Q1 is equal to 1 and C1 is equal to 1. And C1 equal to 1, you have Q0 equal to 1, and of course, it's enabled. So basically, when you have 1, 1, you get C2 is equal to 1. And C3 will be equal to 1 when you have 1, 1, 1. Then C3 will be equal to 1. And C out will be equal to 1 when you have all the Q outputs are all 1s. That's when you get C out is equal to 1. So C out will be equal to 1 if you have the Q output, the 4-bit counter output is equal to 1, 1, 1, 1, and it is enabled. That's when you get C out is equal to 1. Remember this because this is important. I'm going to use it later. Okay? Right. Now, how do I count down? How do I use this 4-bit synchronous counter to count down? Any idea? Students, this is a quiz now. Okay? So you have to answer this question.
Invert Q.
Well, what we need to do is that rather than connecting the Q output, connect the Q prime, Q0 prime, Q1 prime, and so on. Because if you increment the Q prime, you will decrement the Q. So the answer is simple. Increment Q prime, not the Q. So if you increment Q prime, you will decrement the Q. So we can think about actually implementing a counter that will count down, not only count up, but with a small modification, I can make it to count down. Okay, and that's actually shown, of course, in your textbook. You can actually count up, you can count down, you can design a counter that can count up and down. Okay, but you need to understand the basic idea without being lost in the details. Just understand the basic idea. So if you increment Q prime, you will decrement the Q. As simple as that. Okay. Right. So notice that here, okay, this is another implementation of a 4-bit synchronous counter with D flip-flops. So I change here my D flip-flops. Let me clean up everything now. Okay, so notice that I use a 4-bit incrementer here, and I use D flip-flops, D type. Now I would like to change it into T type, T0, T1, T2, T3. So this is a toggle type. So the toggle type already includes the XOR gates, which are shown here. The inputs of the D flip-flops are now part of the T flip-flops. Okay. So I just removed the XOR gates. Is this clear? In other words, when do we toggle this Q0? We toggle this Q0. Let's talk about Q1. Okay. Well, in the case of a Q0, it's very simple. As long as it's enabled, we toggle. Yani one cycle it is 0, the next cycle is 1. Yani 0, 1, 0, 1, 0, 1. That's for a Q0. How about this Q1? We toggle Q1 when it is enabled and the Q0 is equal to 1. So we just have an AND gate here that's going to propagate the carry. So this is C1. Maybe it's clear here. Right. Let me show you this. Okay. And I'll come back to the previous slide. Okay, this is basically the circuit diagram. I just copied it from your textbook. Okay, but I'm showing it. I'm showing it horizontally here. Here it is shown vertically. I think my diagram are better. I'm just joking. Right. So let us take a look here at this. Here, the up count. Okay, so this is a Q0, Q1, Q2, Q3. So notice that Q0, we toggle the value of a Q0 every cycle. 0, 1, 0, 1, 0, 1. That's Q0. So basically, we are toggling it every cycle. So as long as it is enabled here, notice that if it's enable equal to 1, notice that enable is connected here to the T input. So as long as T is equal to 1, we are going to toggle the value of a Q0. Is this clear? That's for the least significant bit of the count. Now, how about the Q1? In the case of a Q1, let us take a look at this table again. It's the same table that I just copied from the ripple counter, but I'm doing it here for the synchronous counter. Now, we toggle, okay, when do we toggle? We go from 0 to 1. Let me just here use my pen tool. Notice that we go from 0 to 1 here. That's when we toggle. Here we go from 1 down to 0. This is when we toggle. This is from 0 to 1, we toggle. So when do we toggle? Students?
When J and K equal 1.
When a Q, do we have J and K? I'm just actually having here, forget about J and K, okay? This is, I'm talking about here toggling the T, okay? The J and K is nothing, okay? I'll talk about it in a minute. Okay, I'm talking about when do we toggle? When do we toggle the value of a Q?
When T is equal to 1?
Exactly. So when do we get this T is equal to 1? Let us see here T1. T1 here we get C1. So basically T1 is equal to C1. T2 is equal to C2, right? And T3 is equal to C3. So when do we get C1 is equal to 1? When it is enabled and Q0 is equal to 1, right? Suppose that's always enabled. So we just always enable. So we make this 1. We fix it to 1. Okay. So when Q0 is equal to 1, then we get C1 is equal to 1 and we toggle. So notice that here in this table, when this is equal to 1, this is 1, this is 1, right? This is when we toggle. If it is 0, we make it 1. If it is 1, we make it 0, and so on. That's actually for a Q1. Type, how about for a Q2? Now notice that the Q2 we toggle here. We toggle here. Again, we toggle here. And finally, we are going to toggle here because all of them are going to be toggled here at the end because we go back to zeros. Okay, we go back to 0, 0, 0, 0. So this is actually at the end. Right. So for the Q2, we toggle when we have a Q1, Q0 equal to 1, 1. Notice that this is 1, 1. Notice that here it's 1, 1. Notice that here it is 1, 1. Okay. So that's when we toggle Q2. When we have a Q1 and Q0 are both 1 and 1. And notice that here we are just using an AND gate. Okay. So therefore, when we have here Q1 and Q0 are both 1 and 1, we have here, okay, Q1 is equal to 1 and the Q0 equal to 1. So we have C1 is equal to 1. And this is equal to 1, which is Q1. So this will give me C2 is equal to 1. And when we get C2 is equal to 1, we toggle T2. So we toggle Q2. So if Q2 was 0, it becomes 1. And if it is 1, it becomes 0. And finally, when do we toggle Q3? Yani when do we make T3 is equal to 1? So when do we have C3 is equal to 1?
When Q2, Q1, Q0 are equal to 1.
Exactly. When all of them, Q2, Q1, Q0 are all 1, 1, 1, that's when I actually going to toggle Q3. So notice that here, when we have 1, 1, 1 for Q2, Q1, Q0, this is when I toggle Q3. It goes from 0 to 1. Also here, when we have 1, 1, 1, this is when I'm going to toggle. It's going to go from 1 to 0 here. All of them will go back to 0. I'm not showing it. I hope this is clear. Okay. So that's how we toggle. That's how we toggle. And this is why I'm implementing it with T-type flip-flops. T-type. So basically the T-type is nothing but the D-type with XOR gates. Okay. So notice how I think about it. I think about it in different ways. Okay, I think about it how when to toggle. So that's what you need to understand about actually counters. So this is one implementation using D type. This is a second implementation using T type. And this is a third implementation using JK type. That's also a synchronous counter with JK flip-flops. Is this clear, students? Notice that for JK to toggle, I have to connect here the J and the K together. Notice the output. This is actually a C1. I'm writing here with my mouse. This is C2, which was shown in the previous slide. The author does not show these details, but I'm just describing this. This is C3. And when you get C1 is equal to 1, you toggle A1. That's basically the Q1 in my previous diagram. Notice that how C1 is connected to both J and K. So when both are 1, 1, we toggle. When they are 0, 0, there is no change. That's a JK implementation. Now, you can actually ask me personally, is there any reason to use JK? لا, this is useless. أنا صراحة باخد هذا السيركت برميه في الزبالة. Okay? Personally, I'm just telling you, is this actually useful with T-type? Is this useful? Yes, this is useful because the T flip-flop uses the XOR gate inside. Is this useful with D-type? Yes, with additional XOR gates. But the JK, it is just for luxury, for the case actually of using JK. هل JK أحسن من الT ولا من الD type? No, it's not better. What is the best type of flip-flop? Is the D type. In my opinion, it's the D type. That's the most common. But who an author, he likes to use actually JK for whatever reason. أنا صراحة I disagree with this author and with this textbook. To be frank with you, from الآخر يعني. Anyways. Okay, you understand my point? The JK is more complex than the T type. Is there an advantage of using JK over the T or the D? No, there is no advantage. Why people have invented the JK is to put it in academic textbooks. Is people actually use in the industry? Do they use actually the JK? No, they don't use the JK. What type of flip-flops they use? 99% of the designs will use the D type. Okay, ممكن a T type, T flip-flop. JK, forget about it. Okay, in your course, okay, in the EE200, they use the JK as number 1. The industry, they use the D type as number 1. Is this clear? If I would like to be an engineer from a practical point of view, do I use a D type or I use a JK? I use the D type. You understand my point? Okay.
Yes.
Okay, so this is a copy of the synchronous counter which was shown in the textbook using JK. He did not show the implementation using the T type. He did not show the implementation using the D type. This is more important. This actually explains the synchronous counter. I just wanted to explain this, and I'm insisting on this because this is very important. Anyways, to understand how you can implement it using any type of flip-flop, it does not really matter. So if I would like to use the JK as a T type, all what I have to do is connect the J with the K, and this is actually what the author is doing. He is using the JK as a T type. Right? Next, timing of a synchronous counter. Now, why we need actually why we say that the synchronous counter is better than the ripple counter? It's based on the timing. Now, notice that the advantage of the synchronous counter is that all the flip-flops are driven by the same clock. All the flip-flops are driven by the same clock. That's the main advantage. And therefore, the outputs are going to have exactly the same delay. So notice that there is a delay here in Q0, which is delta. There is the same delay in Q1. It's also delta. So notice the delay here, the delay here. It's all delta. It's all delta. It's exactly the same delay in all the outputs. Okay. So therefore, all the outputs are going to change at the same time. This is why this is a truly synchronous counter, because it's synchronized. All the flip-flops are synchronized with the same clock. Okay. So here, this is actually the main advantage, is that the delay is delta. Delta here is the delay, okay, in any flip-flop. Any question about this? So this is the timing of a synchronous counter. Now let me tell you actually something which is sophisticated that you can do with counters. Okay, and this is also shown in your textbook. One thing is called frequency division. Frequency division. And if you have a clock with a certain frequency, which is frequency f. So the clock frequency is f. Now, sometimes you have in a given digital system, you have a clock, a system clock. But inside your circuit, you don't really want to use the clock frequency f because it is high. It's a high frequency. You want to use a lower frequency. So you can use a counter as a frequency divider. So you can use a counter as a frequency divider. How do you do this? Well, look at the outputs of the counter. If I'm using a 4-bit counter, look at the output of Q0, look at the output of Q1, Q2, and Q3. They look also like a clock, but they are, of course, delayed by delta. But that's fine. Ignore this delta delay. But look at the shape of the waveform of a Q0, of a Q1, of a Q2, and a Q3. Notice that the clock changes, okay, how it goes up and down every cycle. Now, the same thing for a Q0. It's going up and down, but every 2 cycles. So it takes actually 2 cycles of the clock to have actually 1 cycle of Q0. So we say that the cycle of a Q0 is double the cycle of the clock. Or we can say that the frequency of Q0 is half the frequency of the clock. So Q0 itself, if the clock is always enabled, if the counter is always enabled, and it's always actually counting, you can look at the Q0 output. It has the same shape of the clock, but it has half the frequency. So the frequency of Q0 is f over 2. If you look at the frequency of a Q1 is f over 4. It's the quarter. Okay. So basically, it takes 4 cycles in the clock to have 1 cycle in a Q1. And for a Q2, it takes 8 cycles in the clock to have 1 cycle of a Q2. So the frequency of a Q2 is f over 8. And finally, for a Q3, the frequency is f over 16. Okay, so basically it repeats. Q3 is going to repeat, it's going to make 1 cycle every 16 cycles of the clock to get 1 cycle of Q3. Okay, so basically we can use the counter here as a frequency divider. Yani if I want actually to have clocks with different frequencies inside my circuit, I can do that. So that's basically the idea of frequency division. Questions about this? So that's one application of the counter, is to use it as a frequency divider. Students, are you still with me?
Doctor, we can't get Q3 unless we get Q1, right?
So basically, all of this Q0, Q1, Q2, and the Q3, these are the outputs of one counter. It's a 4-bit counter. It has 4 outputs, Q0, Q1, Q2, Q3. You get all of them. Okay. But if you look at the Q0, okay, it looks like a clock, but with half the frequency. Q1 also looks like a clock, but quarter of the frequency. Okay, so it takes actually 4 cycles to get of the system clock to get 1 cycle in a Q1. So basically it repeats. Okay, so the clock period is actually 4 times the clock period or the clock cycle of the driving clock, okay, of the system clock. If you look at the Q2, the clock frequency is the frequency of the clock divided by 8, and for a Q3. So basically, as the clock is ticking, this counter is repeating. starting from 0, 0, 0, 0. Okay, we have 4 zeros up to 1, 1, 1, 1. Yani this is 15 in decimal. It will be 4 ones in binary, and then it repeats. Yani once it reaches 1, 1, 1, 1, it goes back to 0, 0, 0, 0, and so on. Okay, so therefore you can say that Q3 has a frequency which is f over 16 because it repeats. Okay, so the clock period. So basically it goes from 0 to 16 one time. So this is for a Q3, which is the most significant bit of my count value. So its frequency is f over 16. So every bit of my counter is like a clock, but it has a different frequency. That's the meaning of frequency division. طيب. Okay, now we would like to have some fancy counters. Okay, I would like to design a fancy counter. Yani, for example, I would like to design a counter that does not really count from 0 to 15 and then back to 0. So what we have seen before is a binary counter. Okay, so the binary counter will count from 0 to 15. It's a 4-bit. You can actually have whatever number of bits. So it counted from 0 to 15 in binary, and then it went back to 0, right? That was a binary counter, a 4-bit binary counter. Okay, and we have seen 3 different implementations. Now, I would like to talk about a BCD counter. Okay, I would like to count from 0 to 9, because there are only 10 digits in BCD, from 0 to 9, and then back to 0. Is this clear? That's what I would like to do. I would like to have a BCD counter. How do I do this? Well, we're going to use the 4-bit counter that we have seen before. It does not really matter whether you implement it with D flip-flops or T or JK. It does not really matter. Just look at the counter now as a box, okay, from the outside. So from the outside, that's actually is my 4-bit counter. Okay, it has an enable input. The enable is very important. So as long as enable is equal to 1, you will count. If enable equal to 0, you stop counting. Okay, you just pause or you freeze the count. So the count here is the output of the flip-flops, Q3, Q2, Q1, Q0. This is actually my count value. And there is a clock. And also there is a reset. Okay. Now the clock here, every time you have the rising edge of the clock, we change the count value if it's enabled. So that's a 4-bit. It's a 4-bit counter. Now, what's important to me is this reset. Now, if this reset is synchronous reset, what shall I do to modify this 4-bit counter to become a BCD counter? What's the trick? How do I do this? Yes, Muhammad, تفضل.
Add NAND gate or NOR gate.
Yeah, but what? Okay, so I would like to count from what to what?
From 0 to 9.
Exactly. I need to count from 0 to 9. And the trick is when I reach 9 to go back to 0. So how do I go back to 0? I reset. Hamad, you have a question? Hamad Shabib? You have a comment?
كنت بقول إن Q3 and Q2 or Q1 أوديها للريست.
Like, look at the value of 9 in binary. How does it look like 9 in binary? 1, 0, 0, 1, right? That's actually is 9. Look at the value 9 in binary. صح? So what is 9 in binary? It's 1, 0, 0, 1. Look at the number in binary. It's not that difficult at all. كل فكرة الcounters is just looking at the numbers in binary and figure out how to add a gate, or a gate here, and actually to change the counting sequence. So that's what I would like to show you now. I would like to show you how you can design special counters. Okay. Back here. So the most important thing is this reset. Now, is this reset synchronous or asynchronous? What's the difference between synchronous reset and asynchronous reset? Now, there are 2 different types of resets, by the way, that you can use in counters or in flip-flops.
Asynchronous reset will reset at any given time, regardless.
Immediately. It will reset immediately.
Yeah.
Yes. Whereas synchronous,
it will synchronous based on the clock.
yes, it will wait for the rising edge of the clock, and therefore it will actually synchronize the reset with the edge of the clock. This is very important to remember, and this can make a big difference. Okay, right. So if I would like to implement now a BCD counter using a 4-bit counter with synchronous reset, how do I do this? I need to detect the sequence 1001, right? So how do I detect the sequence 1001? Now, the first time we encounter 1001, notice that the first time we encounter it, we'll have this bit is equal to a 1. This bit here will be equal to a 1. And this bit will be equal to a 1. You agree? Look at the number in binary. حكاية بسيطة منا صعبة يعني. Okay, so look at the number in binary. It's 1001. So focus here on Q3 and Q0 in this example. So once I get here 1 and 1, because I'm counting up. So the first time we encounter 1001, because we start at 0000, the first time we encounter 1001, I will have a Q3 and a Q2 are both 1 and 1 at the same time. Then I'm going to count, I'm going to get the output here. So when I get 1001, in fact, it's enough to have, okay, Q3 and Q0 connected to an AND gate. Then this will give me a 1. And this will give me a 1. And next cycle, at the edge of the cycle, we will reset. We'll go back to 0000. So we are going to skip, okay, we are going to skip from 10 to 15. No, this counter will count from 0 to 15, but we are going to skip from 10 to 15. So once we encounter 1001, then reset and go back to zeros. So that's an implementation of a BCD counter. Now notice that here I'm using an additional OR gate. Okay. Now the reason why I have this OR gate here, so that if I would like to have an external reset, you can reset at any time and start back at 0. Or initially, when you would like to reset your circuit, you can reset and you can start at 0. Right. So that's an implementation of a BCD counter. You can see how simple it is. I can show you large diagrams and so on, but it's very simple. Okay, that's actually implementing it using a 4-bit. Just use the 4-bit counter that we have seen before, add this AND gate and reset, and then go back to 0. Right, what if I have a different type of a reset? Yani many times you have the reset is asynchronous. It's not synchronized with the clock. So typically, you might actually have flip-flops that have the reset is not synchronized with the clock. It's asynchronous. So how do I do it? If I have a different type of a reset, if I have a reset which is asynchronous, what shall I do? Anyone?
Just reset at any time, you know?
No, we want to count from 0 to 9 and then back to 0. We would like to have a BCD counter. So when do I reset? When do I reset? Students, this is a very important question. So I would like now to use a different type of a counter that has asynchronous. Notice that the reset here is asynchronous. So it's not synchronized with the clock. So when we reset immediately. So what shall I do to implement a BCD counter? Okay, with asynchronous reset. The answer is shown, by the way, on the screen.
And not AND gate.
Well, let us just think about it before you add any gate. Let us just think about it, have a strategy to solve this problem before you throw any gate, okay? So you must actually have a way to think about it. So the way to think about it is that do not look at existing solutions. you come up with your own solution. And in order actually to become an engineer, you have to think about your own solution. Do not just copy solutions. People come up with these solutions. Actually, they thought about them. We can also think about our own solution, right? So the idea is here is to count to 10, not to 9. Okay, so the difference is that if you are dealing with asynchronous reset, count to 10. So once you reach 10, because you have to go to 9, and then next cycle, it becomes 10, make the 10 to be 0. Let me repeat. So you count from 0 to 9 normally, and next cycle, okay, you count up to 10, but once you have detected the 10, reset immediately in the same cycle. So let it reach 10 and make the 10 0, reset it to 0. Yani it will jump to 10 and then 0 at the same time, in the same cycle. So that's really now the idea of using asynchronous reset, because if you count to 9 and reset, the 9 will not be counted. It's not really a cycle. You need to have count to 9 and then wait for one cycle to make it 10. And once you have detected the 10, then make it 0. So how do I detect the 10?
Q3 and Q1.
Thank you very much. Yes, you end the Q3 and the Q1. So rather than ending Q3 and the Q0, you end the Q3 and the Q1. Okay, thank you very much. That's it. Okay, and then you reset. So now you can actually see that momentarily you are going to get 1 0 1 0, but then you will see that actually 1 0 1 0 became 0 0 0. So that's actually here a BCD counter, okay, which is implemented using a 4-bit counter with asynchronous reset. Right. Can we build large synchronous counters using smaller ones? Yani suppose I would like to build a 12-bit counter. I can easily do this by propagating the carry out. Remember the C out when I talked about the C out? Now here's the importance of the C out. Now this C out here will be 1 if the counter is enabled. So if this enable is equal to 1, and the Q output is 1 1 1 1. Remember that? Okay, I talked about this in the previous slide. I just would like to reiterate this. So when you get 1 1 1 1 and it is enabled, this is the moment when you get C out is equal to 1. Okay, you get all the carries are equal to 1, and it is enabled. This will produce a C out is equal to 1. Now, this is when you would like to enable the next 4-bit counter. Otherwise, you would like to disable it. So every time you count from 0 to 15, after reaching 15, you enable the next 4-bit counter. So the next 4-bit counter is enabled once every 16 cycles. So every time you count from 0 to 15, you enable the Q, enable the next 4-bit counter. Okay, and then you go back to 0. The same thing here. You enable it once. Okay, use the C out to connect to the next enable and so on. So you start actually cascading these, okay, 4-bit counters, okay, to produce a large counter. So this is a 12-bit counter. You can take here the 4-bit output, okay, and therefore you can produce here 12-bit output. So this will be a 12-bit counter, which is implemented using 3 4-bit counters. So you take the C out and you connect to the enable input of the next 4-bit counter and so on. Notice that the clock is connected to all of them at the same time and reset. You can reset all of them at the same time. So this is a very useful actually counter, okay, a 12-bit counter. It can go here from 12 zeros to 12 ones. 12 with the ones will be 4095, and then you can go back to 0. All are zeros. So you can count here up from 0 to 4095 and back to 0. Now, next time I'm running out of time. Let me actually pause here. Next time I will show you how you can have whatever kind of sequence you would like to have. We'll see also other types of counters. So I'm running out of time. Let me pause here. Okay, and we'll continue inshallah on Tuesday.